So morning, everyone. By the way, it was a really great talk and last talk, and ironically, I'm actually going to talk about machine concepts in JavaScript. So yeah, but it's fine. Like JavaScript is kind of like a language of choice as well. So before I begin my talk, I have some disclaimers to make. So I'm actually not going to talk about machine learning as a science, but more like as a concept. And also, I'm not also going to talk about the details of how to set up a machine learning infrastructure, because all that is a completely different world, completely different story. But I'm just talking about like how us as individual developers or as a small team, about some ideas about how you can get started with of setting up machine learning infrastructure for you to get kickstart your project and then learn along the way. So I'm actually going just to talk about my expertise as a hobbyist. So everything that I'm going to go through here is pretty much something concepts that I learned from my exploration as a hobbyist. So one comparison that actually I want to make is in comparing actually Kill Bill, using Kill Bill. So I'm a huge fan of Kill Bill, and I love to discuss Kill Bill with a lot of my friends. So the common consensus that I've got from most people is that they don't like Kill Bill 1 is awesome, but Kill Bill 2 sucks. So I don't know whether any of you guys feel that way. But for me, having gone through a lot of Tarantino interviews and so on, so how he had written the whole script is actually one entire story. It just got too long. Like I think it was like 6 hours. It was a 6-hour feature length. So he kind of cut it in the middle from like the most interesting parts. So that's why it left you like hanging like at the best part when Uma Thurman destroyed her enemies, and then it comes on to a drastic end. And this is actually my analogy for this is that that's how I'm going to structure my talk. So my first part is I'm going to focus on like the core concepts of machine learning to kind of get you kick-started about, just so that you know what you're doing when you're fiddling with the TensorFlow script. And the other part is pretty much about to discuss about the concepts of how you engineer a machine learning program. So now I'm going to go in the first part about the fundamentals. So a little bit about my background. So I did computer science for my undergrad, but then after I finished my undergrad studies, I actually went on. I worked after working for 1 year, and then I'm like, you know what? Actually, I really want to try out building architecture. So I enrolled in a program in the UK. Where it focuses on using like a computational approach towards architectural design. And during my master's thesis, I actually wanted to tackle the problem of solving the overpopulation in pedestrian stations. And so this is, and I chose Shibuya, the most busiest metro station, to be my case study. So this is an image of like how most people with startup, most students with startup is you go on to try to get as much data about existing circulation as possible, and then this is an image of how I got that data. I did some simulation about how people congest on the platform. And then I went on to analyze all the exits and all the sites to see how different people enter and exit all the different entrances. And then from then on, this is actually just something of my a more experimental approach that I did. So in my undergrad course, I did a course on non-deterministic modeling. What I did might be completely wrong, but back then I was just experimenting with it anyway. So is that having identified all the transition points within the station, I tried to kind of obtain how many people passes through a certain point at a certain time, and then use that to construct a node. And from then on, actually, I would use this kind of model to predict how many people will pass through the different points at different times to make a prediction to identify the bottleneck points to aid in how we redesign the space in architecture. And then, so in the end, after having identified that, my design solution is, okay, so the biggest bottleneck points are the points where there's people who are going in and out at the same time, and that was the points that caused the bottleneck. And then so the best way is to like separate the people through like different flows. So people coming into the station should flow one way, and people going out of the station should flow another way. So that was my final conclusion back then. But actually looking back, this would be a completely perfect machine learning example where we can continuously feed that data in to the station to identify and how the station evolves through the different times and so on. So this experience is kind of like leaves this desire to learn more about machine learning on the back of my mind. And then later on, I went on to become a facade consultant. So in architecture, so what facade consultants do is, so nowadays a lot of architects, they want to propose these crazy buildings, crazy like double curvature buildings. So and a lot, but at the same time, they have no idea how to like basically clad the entire building. And what it will leave is that so you will see this. This is actually one of the projects that I'm working on. It's actually constructed in Shanghai now. So the architect introduced like these you see so on the curved corner points, it's actually a double curved points, and so you see all these like aluminum panels, all these triangular panels. So at the glass, we're trying to restrict them to be of the same length and sizes because that's the most expensive material. But then with the architectural, like the triangular panels, that's the part where it's relatively cheaper that so now let's say they propose you need 10,000 different panels to clad this surface, and then they would have 10,000 different types. So in the factory, they wouldn't want to labor cost is the most expensive part in the factory, and you wouldn't want to have someone going in to measure exactly different dimensions for 10,000 panels. You would want them just group them into let's say a thousand types or even less, 10 types if possible. Then so that's when a lot of the times we would as a facade consultant, we would come in to kind of help them try to optimize the panel configuration so it will be better clad the surface. So I come in and then I would develop a script to think about how to automate in your 3D environment to generate all these panels. I'm not going to go into details, and one of the hardest parts to tackle is the corner bit, where you have a curvature on plan, you have another curvature on elevation. So each floor level is an arc of a different radius, and so if your panel's glass size is, let's say, fixed at 1.5 meters, and then the panel size next to it could be of very, very varying length. So in that case, then actually what I did was a very kind of very a little bit hacky approach in that you develop a script where you will still need to input and guess a figure. Let's say you guess it to be 1.1 meters, and then it will generate all these panels, and then they will define some distance at the very edge. So let's say it maybe has 0.8 meters left, then you need to go back and update the figure to be, let's say, 1.21, and then you continue to go on. So it's a very iterative approach. But looking back, so you still need human input in this to guess the number, which is 1.1 or 1.21 to start with for each floor. But again, it would be great if we can actually have if the system, or if we know how to apply machine learning, then the system can automatically guess which number to start with, or predict which number to start with, and to allow it for you to streamline it to be an entirely automated process. So, but now after my years as a architect, actually, that is the motivation to guide me back into engineering to be back on track as a developer, so I can actually kind of get myself closer to learning machine learning. So first thing first, what is machine learning and why do we need it? Not everything needs to apply a machine learning model. So for example, let's say you made a coffee fetching robot. So so there's two ways for you to kind of set the robot. You can set it to calculate distances and so on to do a certain task. But what if you want the model to kind of be able to think, to be able to identify according to different scenarios? And that's the part when you hit limitations as to how you can program the robot to calculate distances and so on. So that's when you would apply machine learning to train the robot. And the process of training a robot, so have many of you guys played the game of hot and cold, or in some countries they call it like find the thumble? Yeah. So it's like a game where when you're a bunch of kids, they would go out of the room. The kids in the room will one kid would go out of the room, and the other kids would choose an object inside the room. And then when the kid outside comes back in, he will try to find the object. And when he's getting like further away from the object, then the kids would shout like "colder, colder." That means it's the other opposite direction. Oops. So yeah, it's pretty much like in training your robot. Then like when your robot goes away from the coffee, then you would tell like, oh, colder, colder. Then it will know to go the other direction. And then when it gets closer to the coffee, then you just tell it, oh, it's hotter, hotter. And then until the kid or the robot in this case finds the coffee. So the idea, the whole process of machine learning and training your model is pretty much this. It's telling your teaching a model to be smarter, and during the whole process of training a model is teaching a model and giving them identifications that this is you should go the other way. This prediction is completely wrong, and then the model will try to move to the other parts to try to make another set of prediction, and then you would tell them, okay, it's getting closer now, and so on. So I'll explain a little bit further in more tangible terms. So, do many of you, I guess most of you as developers, you have seen Silicon Valley. Yeah, if you haven't, you have to go see it. And I'm sure you will binge watch it in like, 2 or 3 days. It's the best show ever. So here's Xin Yang, one of my favorite characters. So he made, by the way, a bunch of spoilers. So if you haven't seen it, go see it. So in the show, Xin Yang made a hot dog, not hot dog app, and that is a classical model of machine learning. So he had made a classifier or a training. He had trained a model to be able to identify hot dogs or hot dog-like things, and not hot dog-like things. So when later on when Erlich Bachman, his frenemy, goes into tell him to expand it to like basically make a Shazam of food, and that's the hard part when like he now has to extend. So he was like, no, I can't do it. And the main reason is because he has to extend it to classify not just hot dog and hot dog, but he has to expand and train the model to identify all these different foods, and that's the hard part. So the hard part is not coding it. The hard part is taking all the data, feature engineering all the data to identify and train your model. That's the hard part, and that takes time. Yeah. So now let's jump into the ideas of machine learning. So before you go into about like setting up a machine learning system, you have to identify your problem, and as in what type of problem it is. Whether it's a pure classification problem, whether it's spam, not spam, it's a boy or girl, it's a cat or dog, or whether it's a regression problem where you want a tangible value out of it, whether you want to predict housing prices and so on. So it's like a continuous value. So one important concept that you guys will have to understand is the idea of labels and features. So labels are pretty much the thing that you label. For example, in the case of email, whether you want to label an email as spam or not spam. And features are pretty much the parameters, I would say, that you look into identifying whether that email is spam or not spam. For example, you will look into the sender information, you look at what time it's sent, if it's completely out of the person's time zone, you look at the content, and you also look at the keywords, certain keywords like Nigerian prince, then you know it's spam. So the most fundamental goal of machine learning is not improve accuracy. It's actually to minimize your errors that your model makes. That's a very important mindset. So during your whole time, how you evaluate how well your model is doing, is to see how less of an error it produces, not how well it does. But of course, you can also look at accuracy, but the best is to jump in the mindset with trying to minimize the errors. So this is pretty much like an overview how like the training process works. So you would actually have a bunch of labeled featured data. So you have and that is exactly how in the beginning of Gmail I don't know whether you guys remember, Gmail will always ask you guys to label things, whether it's spam or not spam. And that is actually part in feeding onto their database of labeling the features. So so if you identify certain keywords as spam to you, so they will actually feed all that into their model, where the model will start to do predictions. Okay, so by the way, so in your case, let's say you have a bunch of already labeled data, and you feed in your model, like you have a model, and then and the model will make some prediction, and that's the important part when you actually compare the model's prediction with actually the actual labeled data. So for example, like, if 90% of your data is spam, but maybe the prediction comes out to be only like 65%, and in comparing the actual data, then that's when you compute the loss. And then after computing the loss, you would actually go in and update your model, like which is the rates and different parts of your model to for it to improve and to actually retrain again according to your different data. And so in that case, loss is a very, how you calculate your loss is a very important part of machine learning. And that comes with the concept of loss function. So the loss function, so the graph on your left is the one which has a huge loss, because so the blue line is pretty much your prediction results, as compared to the graph on your right, which is more fitted to, the prediction result is more fitted to the actual data. And the loss function is something that you need to define in, so it's something that you use to evaluate how well your model is doing. And so now actually, as JavaScript developers, or well, at least for me as a front-end developer, I tend towards JavaScript. Then JavaScript, TensorFlow.js is actually a very great library. It used to be called Deep Learning JS, but then later on, Google bought it and combined it together with TensorFlow.js. It's basically a deep learning library. It provides a lot of like APIs and so on for you to quickly set up a machine learning training model. And that's actually what my talk or my learning is based on. And here for the my example, I'm going to use like a image recognition example, where it is to identify a bunch of like handwritten numbers to identify them as numbers. So it's a very classical image recognition example. And so so TensorFlow.js is actually the TensorFlow workflow is really straightforward. And so this, by the way, this is actually taken up from their website, where they had like a kind of visualizer for how the process of training model works. And it's great. And I really suggest all of you, before you start tinkering with the API, actually the best thing is to go on it to try and get a feel of the process of training your model. So first you need to prepare your data, and which is all the whole process of labeling your data with your feature and so on. And then you pass all your data into your model. So you build and construct your training model, and then that's when you can, after you've prepared both of these, you can start the training process. And then after you train your model, and then you can use that model to do prediction. So simple 4-step. So the key concept one is data. So there's two types of data. The first type is the data that you use, the labeled data you use to train your model. And the second part, the different types of data is the data that you use to predict to do predictions. So, for example, like in this case where you have all these like labeled examples and so on, and then you pass that into your model to train it. So you input it for training, and then later on, like you can actually, after it's trained up to a certain state when it's actually optimized in reducing the loss, the loss function is optimized. Then you can start trying to inject different types of data for prediction. So one important concept is feature engineering, and the idea of like how you feature engineer your labeled data. So for example, in looking like at housing data, so of course like some data it is a numerical value already. So it's, let's say it's like 3 bedrooms or 4 bedrooms, which is which already you can plug into your model. by the way, the model only takes numerical values in what they call like feature factors. So if whenever there's actually any features that are strings, for example, in email, certain keywords and so on, you have to put that in. You have to kind of like put that into like a numerical factor. And the process of how you convert your numerical your strings into numerical factors is what we call one-hot encoding. And that's the part, for example, here you have Shorebird Way. But let's say we have 100 streets, and you will, in that case, for the factor for that field street name, it will be an array of 100 fields. And like if Shorebird Way is one of them, then it will actually show Shorebird Way, let's say it's the 27th array, and then the 27th array will be number 1, and so on. And so in our case, we are looking at image recognition. So in translating that image to the vector, it will be, let's say we do 28 pixels by 28 pixels. So the last, so it will be an array of 28 versus an array of 28, and 1 is like the color level. Here we do black and white, so it's just only 1. And that's how you define your input shape. And another important concept with data is that there's the idea of training sets versus your test set. Training set is pretty much the set of data that, so let's say you got 10,000 data points. You need to segment out a part of your data to actually, as your test set, to test how well your trained model is doing. And that's, here 80% or 20% is just a rough figure. You can change it to 90% or 10%. But normally most people do it 80 to 20. So the first step in preparing your data, which is called the data preparation, is pretty much you need to load and prepare your data. You need a deck of cards, you need to shuffle your data. You need to split your data into training batch, test batch, and then you define also, in your JavaScript file, you just define the functions to fetch your training set and your test set. And the second part is the model. So the model is it's a neural network. So a neural network is pretty much taking reference to the most intelligent mode of communication in the world, pretty much our neurons. So how our neurons communicate with each other is the act of firing signals in a word, whether a neuron is activated or not. And in clicking on this concept, the artificial neural network is pretty much also taking in let's say your data, and then you apply an activation function to see whether that node is activated or not. So a linear regression. So linear regression is pretty much a sum of the weight, input, and bias. But in most cases, especially in our case, it's not a linear regression. So it's a non-linear transformation in which you will need to apply an activation function in order for each node in order to let them know whether they need to be activated or not. This is actually a very hard mathematical or scientific concept, which I highly recommend most of us to go deeper into the topic when the time comes. And there are many different types of activation functions. So the most typical part is the binary classification, whether a node is simply just activated or not activated. But from my reading, almost everyone recommends the ReLU as an activation function. There's a huge bunch of ideas behind why ReLU is the best. I'm not going to go through it in details here, but pretty much ReLU will allow you to basically provide a continuous set of values to calculate the probability of your different different classifications. So which I'm going to explain a little bit more in detail. So this is the visualization of a neural network. So you have your input data, input layer where you pass in all your middle hidden layers, and that's when all your nodes, whether you pass all your nodes with activation function to decide whether something is activated or not activated, and so on. And then with the output layer. So in our case, the output layer is actually pretty much an array because we identify numbers from 0 to 9. So it's a class. It's a case of categorization, whether the probability of whether that image is a 0 or probability of a 1 or 2 or 3. So let's say you input an image that's a number 6. The number 6 in your output layer should have the highest probability, and that's when you deduce prediction is of number 6. So all the stuff in TensorFlow is just literally it's just this, TF plus sequential, and that's how you set up your model. So in our area, it's a convolutional model. So the main idea is how do you translate an image to vector? And that's when you apply convolution, where it will actually go through the act of like scanning through your image to deduce it into like a 28 by 28 vector. And the idea of, again, like you pretty much taking on that, you go through a convolution of your image, you go through your value layer, your hidden layer, and then you also apply max pooling. You apply max pooling to it, and within your model, you go through all these hidden layers to deduce a result, which is a set of probability. Here, that's again, you cannot do it with an infinite amount of results. You can only identify within like 4 different types of image, whether it's a flower, whether it's a cup, whether it's a car, whether it's a tree, and then that's how you train it. And the outcome is the probability of how likely it is to be a flower, and so on. So this is how it will look like in TensorFlow. In each layer is pretty much what you do here, which you do your convolution, you apply it, a value activation function, and you also conduct max pooling on your layer. And so it's just a matter of like how you power on the layer. So we're a little bit running out of time, so I'm not going to explain about max pooling, but it's just something that they will actually do to aggregate the probability among like each so each 4x4 image, then you take the highest probability and you multiply and so on. So one idea is whether you want to add more layers. Does it mean it's better in that case? But actually not really, because you don't want your model to be too trained to your set of data. So there's the idea of like overfitting, where like your model does not react well with new incoming data. It's just too fit for that. So as in like it will only look at, for example, in your case, it will only identify these pixels as flower, but in many different cases it's not. So you don't want to overtrain your model. So the next part is the whole process of how you train your model. This is actually pretty much the earlier diagram that I showed you about training in more tangible terms, where you feed your model in. Your model will actually apply the weights, which is pretty much what the activation function does, and then it will train your model. It calculates the loss, and once it calculates the loss, let's say in the beginning, of course, it will suck in terms of its prediction, and that's when the loss function comes in. It will calculate, the derivative of your error and do backpropagation to update all the nodes, and then that's when you continuously repeat the process again to train your model. So in TensorFlow terms, what you need to do, pretty like all this idea behind, you just need to simply define, like configure your model to configure with an optimizer, the loss function. There's many different types of loss function. Here it's a pure classification problem, so you use categorical cross entropy. You also define your evaluation metric. It's pretty much how you evaluate how accurate your model is, and all this together will compile your model. So so this is pretty much like how when it comes together when you run it, and then so now the model is in the back. It's like training all your data. It's loading your data. You start doing this whole process of training and backpropagation. So you can see while it's training, the loss, according to the loss function, the loss is decreasing while your accuracy is increasing, and that's when it starts to do all these predictions. Of course, you still can't get 100% prediction, but in this case, it's trained to a certain way that maybe it can get like 90% of the predictions right. So, okay, so all that theory behind is interesting, and it's enough for us to kickstart. But we as developers, of course, we want to build things with it. And that's an important part where machine learning engineering comes in. So all that stuff that I talked to you about, you have a data.js file to prepare your data, you have your model.js file to model your data. And then that's just only the big picture. Where as a front-end engineer, front-end developer, all this stuff will exist in, let's say, the front-end in your React library and so on. And then all this stuff, can translate into our modern tools for development. So one important idea is static versus dynamic. So static system, pretty much as what the name suggests, is you will actually train on pre-existing data. So you train a set of data, you plug that model, you can plug it in an offline environment, let's say just your browser, and you can use it to train and make predictions. But a dynamic system is something that actually is connected to your server or to the cloud or anything. It's a training model that consistently get new featured and trained data and update and continuously run that training model. So static system, pretty much, yeah, client side and dynamic, you need a server. So here, I have hacked together a quick demo of basically how offline how offline prediction works. So this is a simple React component. Everything is done on the browser side. So and here I'm using a toxicity classifier. It's a pre-trained model that you can easily just grab from the TensorFlow website. And I made something that what I call Trollbuster. So as you're going on site, how are you feeling? I feel bad. So let's say I type, whoops, shut up. By the way, Anarchy, sorry, I might break your code of conduct. Shut up, moron. I'm trolling the site. And then what it does is everything is done on the client side. So here you input shut up, moron. Sorry, yeah. And then that's when, that is exactly how what it will return to you is you will actually have your results that will give you all the probabilities, whether it's, you have all these like categories. You have your identity attack, insult, obscene, and so on. And it will actually try to identify which category is a match and how great of a probability it will fit into that. And for example, if you want to type I had a wonderful day, and then it will basically, again, everything is on the browser side, so it depends on your browser, on your system, and then but then now everything is perfect, and it will identify everything as false, and then it will allow you to submit your data. So that is one example on the client side. And actually, I am completely running out of time. So here, I was hoping to go through an app idea about how you can set up your infrastructure on the static and dynamic systems with Redux and TensorFlow. But I guess I can quickly, if you guys are interested in knowing more details about how to set it up, you can come to me. But pretty much on a static side, you do all your machine learning code on the browser, and you can just simply use Redux to fetch and dispatch your actions from your TensorFlow file that's hosted on the client side. And then on demand, actually, GraphQL will be a really great tool for for dynamic systems where you, during the initial stage, you can continuously send mutations of the user's preference to your server to train your model. And after the model is trained, then you will continuously you can set up while you send predicted results from the server, the user's interaction, you can continuously, let's say you can send in mutations from your user's interaction continuously to your server to see how a user interacts with a thread and so on to update the prediction. So, yeah. So my last word is, so of course we are engineers, so we we are not data scientists, we can make the perfect training model. But for us to approach machine learning, we should just approach it as the great engineer we all are, but not the machine learning expert we aren't. So there's a lot of resources out there and a lot of that's already provided for us to immediately quickly go in and hack a machine learning system. So, and for us, we can also focus on how we will engineer the machine learning system. So I'm so sorry I completely overran. If you guys have more questions, you can come grab me in the corridor and so on. Hi.